In this video, we're going to discuss software-defined networking, or SDN, and OpenFlow. Now, one of the hardest things to understand with SDN, or software-defined networking, is the various definitions of SDN. Martin Casada, the gentleman who's seen as the father of SDN, or software-defined networking, was asked, what is SDN? And he said, well, he's not sure anymore because its definition has changed. It's kind of like an umbrella term for various ways to use software to manage and manipulate networks. For this discussion, I'm going to explain three main views of software-defined networking. The first definition is open SDN, typically using a protocol called OpenFlow. The second definition is SDN via APIs, or application programming interfaces. And the third way, or third definition of SDN, is SDN via overlays. The Open Networking Foundation, which is the organization in charge of the OpenFlow protocol and OpenFlow standard, defines SDN as the separation of the control plane and data plane, where the networking devices are controlled or updated using the OpenFlow protocol. That is one definition of SDN. Cisco, as an example, likes to use the SDN via API model, where functionality on networking devices is exposed using a rich application programming interface, or API. Developers can manipulate network devices using a richer API than was possible using, for instance, the CLI and SNMP. So networks can be programmed using a richer or extended application programming interface. VMware use SDN via overlays, where, for example, VXLAN tunnels are used across a network infrastructure. For the ATP course, we're going to concentrate on the Open SDN model using OpenFlow, but I will explain the other visions of SDN briefly. In a traditional environment, where, for example, a company has 3 switches or 3 routers, each device has a local control plane and a local data plane. Now, the control plane is essentially the brain of the device. A device with a local control plane has, for example, a local routing table or local RIB, routing information base. Protocols like OSPF are configured on these devices to update the routing table. Open Shortest Path First, or OSPF, is a distributed routing protocol that is run on each device and exchanges routes between the devices to allow them to work out what the topology of the network looks like. OSPF is a complicated distributed routing protocol. In a traditional environment, the control plane runs locally on each device. In other words, each device has a local brain. Advocates of SDN will say that this is a complex way to work out the topology of the network. There is no single device that has visibility of the entire network. Each device has to work out independently what the network looks like, and together they synchronize a link state database, which is the state of the topology at a given point in time. If you have multiple network devices, from a management point of view using the CLI or command line interface, you would have to connect to each device and individually and typically manually configure that networking device. Each device also has a local data plane. The data plane is how packets are forwarded through the device. So, if you had 3 switches, each switch has a local control plane. The local control plane is the local brain once again. Each device also has a local data plane. This is used for forwarding of the traffic. So how is the traffic forwarded through the device? So in other words, traffic arrives on port 1, it needs to be forwarded out of port 2. That information is programmed using the control plane in a routing information base as an example, or a MAC address table where the device learns where MAC addresses are on the topology. That information can then be pushed into hardware, into the data plane. So the control plane is typically run in software. The data plane is a copy of the routing table, as an example, run in hardware to allow for high throughput forwarding of traffic from one port to another. From a management point of view, each device has its own management plane. In other words, you need to configure each device individually. If you had 100 switches or 100 routers, you would have 100 control planes or 100 separate brains. You would have 100 data planes, and you would have 100 management interfaces to manage those devices. You would need to telnet or connect to the CLI of each of those 100 devices to configure OSPF or to configure spanning tree, as an example. Another problem that limits automation of networking devices is the fact that every device has its own proprietary operating system and own proprietary interfaces. If this device was an HP Comware switch, and this device was an HP Provision switch, and this device was a Cisco switch, and you had some other devices from Juniper and other networking vendors, it's very difficult to create an application or a new routing protocol that is installed on every one of those devices. So as an example, if I developed a new routing protocol, David's Dodgy Routing Protocol, DDRP, which I think is a very good routing protocol, it would be very difficult for me to get vendors such as HP, Cisco, Juniper, and others to run this new routing protocol that I've developed. There is no open interface on these devices that allow me to change the control plane and hence the data plane of these switches. I can't develop a new routing protocol and just install it on these switches. The operating system on these switches is proprietary. I have no access to the operating system. I can't change the operating system to install a new routing protocol. I can't change the APIs or interfaces on these devices because it's proprietary. So advocates of SDN and OpenFlow will say that this limits innovation. It would make much more sense to open up the networking devices to allow other people to develop applications, protocols, and utilities that allow for rapid development and innovation in networking. On the other hand, when you look at server technologies and server development, there has been rapid innovation in the last 10 years. Networking has been stagnant. We still configure OSPF in the same way today as we did 10 years ago. But if you think about PCs or servers, I, as an application developer, could write an application, any application, something like Microsoft Word, or a game, or some kind of application that's specific to a business requirement. I would write that application for an operating system such as Windows or Linux or some type of OS. This operating system abstracts the physical hardware from me as an application developer. If I was running an application and installing it on an HP laptop or a Dell laptop or a virtual machine running in VMware or in VirtualBox or many other types of physical implementations, I as an application developer do not need to be aware of the network interface cards used on these physical machines or virtual machines. I literally write an application to an API for the operating system, and the operating system hides the complexities of the network interface card, the memory, and other physical characteristics of the hardware. I, as the application developer, are unaware of the physical server that my application is installed on. The rapid developments of VMware and other virtualization technologies have allowed the industry to extend this where the operating system doesn't even know which hardware it's physically installed on. You can rapidly move a virtual machine from one hardware platform to another. So in other words, I could create a virtual machine on my laptop, which may be an HP laptop, but you could install that on an Apple Mac running within a VMware virtualized environment. That is because of abstraction of the hardware from the application. That doesn't exist in networking today, however. So in a server environment, I could create an application, talks to an abstraction layer or operating system such as Windows. Windows hides the complexity of the hardware that the application is installed on from me as the application developer. I don't have to be concerned about the physical hardware that my application is installed on. I can write my application in a high-level programming language such as Python or Visual Basic. I am unaware of and don't need to be concerned about the physical hardware that the application is run on. That is not possible today in networking. I cannot create an application that's installed on networking devices because this is proprietary. I have no access to the vendor operating system code to make changes. So with OpenSDN and OpenFlow, the idea is to create an open interface on networking devices and create an abstraction layer to allow for rapid application development. So this situation changes to the following. So what we introduce here is a controller or abstraction layer. The controller talks to the networking devices using an open standard protocol, in this case, OpenFlow. OpenFlow provides an open API or open interface to networking devices. The idea is it doesn't matter which operating system or vendor the networking device is using, there is an open interface to managing the flow table of that device. This is known as the southbound API. On the northbound API, we have two interfaces, one using the RESTful API and the other one using the Java API. These are two interfaces that allows an application developer to manipulate flow tables and flow entries on networking devices without communicating directly to those networking devices. The application developer is abstracted from the hardware and doesn't need to be aware of the details and requirements of physical ASICs on switches and networking devices. The application developer, just like in Windows, uses a high-level API, in this case a REST or Java API, to communicate to the controller, and the controller takes care of the nitty-gritty or complicated details of updating flow tables on switches. So previously we had 3 switches, each with a local control plane and local data plane. In an OpenFlow SDN environment, we have a controller, and in its purest form, the brain of the networking device is moved to the controller. So rather than the networking devices each having their own brain, there is now a central brain in control of the networking devices. This provides a centralized device for centralized control, centralized policies, and easier management. As an analogy, and it's only an analogy, in a wireless environment, previously we had autonomous access points. So you might have had 100 autonomous access points. These days we have a lightweight or controlled access points where 100 access points are controlled by a central controller rather than each access point having its own local brain. It's much easier to manage 100 access points using a centralized controller than it is to manually create policies on 100 individual access points. So that's similar to the idea here, where we have a centralized controller that is pushing policies or configuration changes down to networking devices. It also allows an application programmer to create an application that can manipulate the flow of traffic on the network. So I could create an application that sends a command through the REST API to the controller, which then updates the switches using OpenFlow, that now says that traffic arriving with a MAC address of A going to a MAC address of B should flow through the network along this path. Now, there are some optional videos that I've added to this training where I actually show you a application, in this case a very simple application, a bash script, updating the flow tables of the switches and manipulating the flows of traffic in the network. That can be extended to far more complicated applications, and I'll talk about some examples in a moment. But to summarize, in Open SDN, or SDN using OpenFlow, the networking devices no longer have a local brain. So in its purest form, so pure Open SDN, the brain is removed from the networking devices and is put into a centralized controller. The switches use what is called a flow table that contains flow entries. Flow entries are updated by the controller, but the controller is in actual fact just a conduit or an abstraction layer that allows application developers to manipulate the flows on the network. The power of SDN and OpenFlow comes into play with applications. You or I could write an application that sends commands to the controller, which in turn uses OpenFlow to update the flow tables of the switches, which in turn manipulates the flow of traffic in the network environment. That's very difficult to do in a traditional networking environment. So just to reiterate terminology, and then I'm going to talk about an example application that HP have developed. We have an application. It uses the northbound API to communicate to and update information on the controller. The controller uses the southbound API to update the flow tables of networking devices. Typically, we talk about switches, but these, in the greater vision of things, could be routers, load balancers, firewalls, and other devices. Northbound API typically uses a RESTful API or a Java API to allow changes to the networking environment. On the southbound API, in a pure OpenFlow environment, we use the OpenFlow protocol to update the flow tables of switches. Now, in other environments, such as using SDN via APIs, different protocols could be used on the southbound API. So something like netconf or OpenFlow or SNMP or other protocols could be used to change the configuration and update the flow tables of switches. OpenFlow does not update the configuration of devices. So in other words, it doesn't do things like configure OSPF or configure usernames on the switch. It updates the flow tables of the switches to manipulate how traffic flows through the networking environment. There is a protocol that would allow you to change the configuration, but that's not widely supported, so a lot of vendors are now using SNMP, netconf, and other protocols for updating the configuration of the networking devices. This tier here is called the application layer. This is called the control layer, and this is called the infrastructure layer. So application layer is where your applications reside. They use the northbound API to talk to the control layer, which in turn uses the southbound API to communicate to the infrastructure layer of an SDN environment. So applications are in the application layer, use the northbound API to talk to the controller, which in turn uses the southbound API to communicate to networking devices. Application layer, control layer, infrastructure layer, northbound API, southbound API. We also have east-west traffic, And all that means is you have multiple controllers and they communicate with one another. So southbound is controller down to infrastructure or networking devices. Northbound is between the applications and the controller. East-west is between controllers in the control layer. One of the applications that HP have developed is the HP Network Protector, and you may see it referenced as Sentinel. Sentinel was an old name for HP Network Protector. Now, what this application does is it essentially intercepts DNS queries and then checks those DNS queries against a tipping point database to ensure that users are not going to bad websites or malicious websites. And this implementation uses OpenFlow. So the way it works is the Network Protector application is installed on the controller and uses the Java-based API for communication to the controller. The application also references a copy of the tipping point database, which contains over 1 million website entries, allowing the application to leverage this database of malicious or bad websites. The controller uses OpenFlow to update the switches to intercept DNS queries. So if a PC is in the network and sends a DNS request for a bad website, such as piratesmustdie.com. That is a bad or malicious website. So the DNS query for piratesmustdie.com arrives at the switch. This application, using the Java API to the controller, has already pre-programmed a flow entry that says when the switch receives a DNS query, send it to the controller. So when the PC sends the DNS query for piratesmustdie.com, that DNS query is sent to the controller, which in turn sends it to the Network Protector application. The Network Protector application checks the tipping point database to see if this is a malicious website. And in this case, it is a malicious website. So that is returned back to the application saying bad or malicious website. The application then sends a message back onto the network to inform the PC that this domain doesn't exist. So essentially, the PC believes it has received a response from a DNS server saying non-existent domain. But in actual fact, what's happened is the DNS query has been intercepted and checked against the database. And in this case, because it's a bad website, the Network Protector application has fabricated a DNS response, sent it back to the PC saying non-existent domain. The PC therefore does not attempt a connection to this domain because it doesn't exist. Now, if a DNS request arrived for a good website, let's say hp.com, that gets sent to the controller. The controller in turn sends it to the application. The application checks the tipping point database and sees that hp.com is not a bad website. So what happens is the DNS response is simply sent back to the network and is forwarded to a DNS server for normal resolution. So the DNS server on the network receives the request and forwards back a reply, and the traffic proceeds normally. In this case, we are using something called hybrid processing, where the switch has its own local brain and is not a totally dumb device or pure OpenFlow switch. In this example, a specific flow entry is programmed on the switch to intercept DNS queries. The switch isn't made a pure OpenFlow switch or a dumb switch, for lack of a better term. Another term you may come across is OpenStack. So what is OpenStack? It's a collection of open source software projects that enterprises and service providers can use to set up and run their cloud, compute, and storage infrastructure. This was originally set up by Rackspace and NASA, but the foundation has attracted many members, including HP, Cisco, and others. On the OpenStack website, openstack.org, there's a quick overview of what OpenStack is, who's behind it, who uses OpenStack, and why open source matters. Please refer to the openstack.org website for more information about OpenStack. For this course, we're just briefly mentioning the term so that you're aware of what OpenStack is. In brief, it provides an open framework for interacting with pools of compute, networking, and storage resources and provisioning these on demand. Corporations, service providers, researchers, and global data centers are implementing OpenStack today to deploy large-scale cloud deployments for both private and public clouds. For more information about OpenFlow, please visit the Open Networking Foundation website found at opennetworking.org. Under SDN Resources, you can find out about OpenFlow and view the OpenFlow switch specification, where there is great detail explaining, as an example, that a controller uses the OpenFlow protocol to communicate with a OpenFlow switch. An OpenFlow switch has an OpenFlow channel for communication to the controller. It contains one or more flow tables, which can be updated to manipulate the flow of traffic through the network. In the demonstration videos that are part of this course, I show you practical examples of this taking place, where OpenFlow rules are programmed to match certain types of traffic and then take an action such as forward the traffic out of a certain port, as well as keep counters or statistics of the number of packets that have matched a flow entry in the flow table.